Hey YouTube, Clarity TV here. This is the second part of the video where I left off before my own data cut me off. So at the first, this approach was of limited practical use, and in the 1960s and 70s it remained largely confined to the fringes of the field. Then the computerization of many industries and the emergence of large data sets renewed interest. That inspired the development of more powerful machine learning techniques, especially new versions of known as the artificial neural network. By the 1990s, neural networks could automatically digitize handwritten characters. Amazing stuff, the evolution of technology and the evolution of cells. Link these two, think about those. But it was not until the start of this decade, after several clever tweaks and refines, that very large or deep neural networks demonstrated dramatic improvements in automated perception. Deep learning is responsible for today's explosion of AI. It has given computers extraordinary powers, like the ability to recognize spoken words almost as well as a person could, a skill too complex to code into the machine by hand. Deep learning has transformed computer vision and dramatically improved machine translation. It is now being used to guide all sorts of key decisions in medicine, finance, and beyond. This is amazing stuff, guys. Well, the workings of many machine learning technology are inherently more opaque, even though computer scientists, than a hand-coded system. This is not to say that all future AI techniques will be equally unknowable, but by its nature, deep learning is particularly dark black box. You can't just look inside a deep neural network and to see how it works. A network's reasoning is embedded by the behavior of thousands of simulated neurons, arranged in dozens or even hundreds of intricately interconnected layers. The neurons in the first layer each receive an input, like the intensity of a pixel or an image, then perform a calculation before outputting a new signal. These outputs are fed into a complex web to the neurons in the next layer, and so on, until an overall output is produced. Plus, there is a process known as a back propagation that tweaks the calculations of individual neurons in a way that lets the network learn to produce as desired output. The many layers in a deep network enables it to recognize things at different levels of abstraction. In a system designed to recognize dogs, for instance, the lower layers recognize simple things like outlines or color. Higher layers recognize more complex stuff like fur on our eyes. And the topmost layer identifies it all as a dog. The same approach can be applied, roughly speaking, to other inputs that lead a machine to teach itself the sounds that make up words in speech and letters, words that create sentences in text, or steering wheel movements required. Indigenous strategies have been used to try capture and thus explain in more detail what's happening in such systems. 2015, researchers at Google modified a deep learning-based image recognition algorithm so that instead of spotting objects in a photo, it would generate or modify them. By effectively running the algorithm in reverse, they could discover the features the program uses in recognizing, say, a bird or a building. The resulting images, produced by a project known as Deep Dream, showed grotesque animal-like animals emerging from clouds and plants, hallucinatory pagodas blooming across forests and mountain ranges. The images proved that deep learning needed to be entirely inscrutable. They revealed that the algorithms home in on familiar features like birds' beak or feathers. The images also hinted at how different deep learning is from human perception, in that it might make something out of an artifact that we would ignore. Google researchers noted that when its algorithm generated images of a dumbbell, it has also generated a human arm holding it. The machine had concluded that the arm was a part of the thing. Further progress has been made using ideas borrowed from neuroscience and cognitive science. A team led by Jeff Clune, an assistant professor at the University of Wyoming, has employed the AI equivalent of optical illusions to test deep neural networks. In 2015, Clune showed how certain images could fool such a network into perceiving things that aren't there. Because the images exploit low-level patterns that systems search for, one of Clune's collaborators, Jason Yazinski, also built a tool that acts like a probe stuck into a brain. His tool targets any neuron in the middle of the network and searches for the image that activates it the most. The images that turn up are abstract. Imagine an impressionistic take on a flamingo or a school bus, highlighting the mysterious nature of the machine's perceptual abilities. Amazing stuff. We need more than a glimpse of AI's thinking. However, there is no easy solution. It is the interplay of calculations inside a deep neural network that is crucial to the higher level pattern recognition and complex decision making. But those calculations are a quagmire of mathematical and functions and variables. If you had a very small neural network, you might be able to understand Jakula says. But once it becomes very large and it has thousands of unit layers per layer and maybe hundreds of layers, then it becomes quite ununderstandable. Complexity. Humans, brains, same thing. Layers and layers and layers. In the office next to Jacola is Regina Barzalay, an MIT professor who is determined to apply machine learning to medicine. She was diagnosed with breast cancer a couple of years ago at age 43. The diagnosis was shocking in itself, but Barzalay was also dismayed that the cutting-edge statistical and machine learning methods were not being used to help with oncological research or to guide patient treatment. She says AI has huge potential to revolutionize medicine, but realizing that potential will mean going beyond just medical records. She envisions using more of the raw data that she says is currently underutilized. Yeah, I mean, we've had these technologies for years. We just haven't applied it. So that means that any technology, any trend, any pattern in the future is going to be that exact possibility and potential where there's going to be underutilizations of what we already have. Imagine, think about the things you do have. What can you do with them right now that could bring you closer, right? We all have the tools to make our dreams come true right now. Imagining imaging technology, pathology data, and all this information. After she finished cancer treatment, last year, Barzalay and her students began working with doctors at Massachusetts to develop a system capable of mining pathology reports to identify patients with specific clinical characteristics that researchers might want to study. So exactly, take a whole bunch of patients, test subjects, scenarios, circumstances, putting them all together over an amount of time, taking the data points and plotting it. The US military is pouring billions into the project that will use machine learning to pilot vehicles and aircraft, identify targets, and help analysts sift through huge piles of intelligence data. Here, more than anywhere else, even more than in medicine, there is a little room for a logarithmic mystery, and the Department of Defense has identified explainability as a key stumbling block. David Gunning, a programmer manager at the Defense Advanced Research Projects Agency, is overseeing the aptly named Explainable Artificial Intelligence Program, a silver-haired veteran of agency who previously oversaw the DARPA project that eventually led to the creation of Siri. Gunning says automation is creeping into countless areas of military. Intelligence analysts are testing machine learning as a way of identifying patterns in the vast amounts of surveillance data. Many autonomous ground vehicles and aircraft are being developed and tested, but soldiers probably won't feel comfortable in a robotic tank. It doesn't explain itself to them. Analysts will be reluctant to act on information without some reasoning. Indeed, it's often the nature of these machine learning systems that they produce a lot of false alarms. So an Intel analyst really needs extra help to understand why a recommendation was made. I mean, we need to make sense of things before we send a fucking missile to goddamn village now, right? This March, DARPA chose 13 projects from the academia and industry for funding under Gunning's program. Some of them could build on work led by Carlos Gustron, a professor of the University of Washington. He and his colleagues have developed a way for machine learning systems to provide a rationale for their outputs. Essentially, under this method, a computer automatically wants to explain itself. It finds examples from datasets and serves to sum up a short explanation, essentially. A system designed to classify an email message as coming from a terrorist, for example, might use many millions of messages in its training and decision-making. But using the Washington team's approach, it could highlight certain keywords found in a message. Gustron's group has also devised ways of an image recognition system to hint their reasoning by highlight their parts of an image that was more significant. Okay, now one drawback to this approach, and others like it, such as Barzalay's, is the explanation provided would always be simplified, meaning some vital information may be lost along the way, because we haven't mapped everything in the body yet, right? In our potential cases. So we haven't achieved the whole dream, which is where AI has a conversation with you, and it is able to explain, says Christian. We're a long way from having truly interpretable AI. Most absolutely. Incredible stuff. It doesn't have to be a high-stakes situation like cancer diagnosis or military maneuvers for this to become an issue, okay? Knowing AI's reasoning is also going to be crucial if the technology is to become a common and useful part of our daily lives. Tom Gruber, who leads the Siri team at Apple, says explainability is a key consideration for his team as it tries to make Siri a smarter, more capable virtual assistant. What if it lies to you? Gruber wouldn't discuss specific plans for Siri's future, but it's easy to imagine that if you receive a restaurant recommendation from Siri, you'll want to know what the reasoning was. Ruslan Salaktudinov, Russian probably, director of the AI research at Apple and an associate professor of Carnegie Mellon University, says explainability is the core evolving relationship between humans and intelligent machines. It's going to introduce trust. That's exactly what it's all about, isn't it? So, essentially, just as many aspects of human behavior are impossible to explain in detail, perhaps it won't be possible for AI to explain everything it does. Even if somebody can give you a reasonable sounding explanation for his or her actions, it probably is incomplete. The same could be very well for true AI. Says Clune of the University of Wyoming, it might just be part of a nature of intelligence that only part of it is exposed to rational explanation, some of it just instinctual or subconscious or inscrutable. Exactly. It might not be true. What a machine has, it might be like a child who doesn't know the truth because, I mean, it just says what it knows best, right? It might repeat a lie that it was told. But with the explainability factors that are trying to program in, this is a fantastic thing and this is the way forward. But again, the dangers. What if a machine decides to lie to you? Anyway, this has been Gustav Becker with Clarity TV. Have a fucking awesome day. Yeah.